Okay, we're going to do topic of 8.11 in the AP Calculus curriculum today, volume of the washer method revolving around the X or Y axis. Calculating volumes of solids revolution using definite integrals. This time we're going to use solids revolution around X whose cross sections are ring shaped or may be found using definite integrals with the washer method. We'll start by just explaining the geometry behind this washer method. This first video, we'll do this in 3 parts. So what we're looking at is if we have a washer method, if we take a function f of x and a function g of x, and those two functions create a region, or if we were going to revolve this region around the x-axis, it would create what we looked like more like a washer than a disk. We've been doing the disk method where we took a rectangle in here. Actually, we took a rectangle that went all the way to the x-axis, right? And we revolved it around the x-axis. And it gave us this entire disk. If we took that disk out, then we had a width that was g of x units high, or in radius, and it was, the height was dx. But now what we're doing is we're only revolving part of that region around. But we can look at it as if we're involving the entire region around first, and then cutting out the smaller region. If I did the disk method with the f of x, then what that would effectively be doing is taking a center portion out of this disk, where the radius of that inside disk is f of x. The height is still dy, but what we create now, instead of a big disk like we had before, is why this is named what it is, a washer. So that if you looked at it standing up on its side, it would look like a donut. And this middle portion here is cut out. And that is that part f of x. Because of the properties of integrals, we can get this, let's see, by doing the volume of the outer ring. So the volume of the top function let's say the big disk is equal to pi times the radius squared times dx. And the radius in this case is g of x squared, so it's pi times g of x squared dx. And the volume of, we would get the volume of the entire thing by integrating. That was one disk, the big disk. So here, if this was A, x equals A, and x equals B at those points of intersection to find a region, we would integrate from A to B. Pi would come outside, and it would be g of x squared times dx. And then we would get the volume of the inside ring that we'd taken out. We would take it away from that, and we would get from A to B the integral. Pi would again come outside. This time, the inside radius would be f of x, so we would have f of x squared. Let's go ahead and write the expression for that up there. We've been doing that. It's pi times f of x squared, the radius squared, dx. And now, because of properties of integrals and a little bit of factoring, if we factor the pi out front, then we can say that's the same as the integral from a to b of g of x squared times dx minus the integral from a to b of f of x squared dx. And because of properties of integrals, that becomes pi times the integral from a to b. Remember, the integral's a linear operator, means the difference of two integrals with the same limits of integration can be the integral of the difference of those two functions with the limit. So this becomes, whoops, is g of x first. G of x squared minus f of x squared all times dx. And that's how we generate the volume of the region that would end up looking like a washer if we revolve that region around the x-axis. And this interior part would be cut out. And so we would have our washer. And that's what the washer method is. That's the geometry behind it. This is the formula, general formula, where top function squared minus the bottom function squared is your integrand. Integrate from a to b, the boundaries for the region, and multiply it by pi. All that becomes because we have basically one large disk where the volume of that one large disk is pi times the upper function squared times dx minus the volume of a smaller disk that we cut out and bring out, which is pi times the smaller function squared, the lower function squared times dx. And the properties of integrals, let's bring that into one thing. I prefer not to memorize this formula. I prefer to use the geometry to think through this problem, just because we can introduce problems that are very, very different. And that way we consider each region, especially if these curves or these regions are defined by more than one intersection, we need to be sure and apply the geometry. But this is basically how we do it. And if you're into memorizing formulas, this is the formula for the washer method.